Hi everyone, we are Group 7 for Digital System. Our team consists of Amrel, Chin, Elgin, Care and Carlson. We are here to walk you through the essential of digital IC design and simulation. Let's kick things off with the microelectronic chip. It is a tiny semiconductor wafer that packs in millions of components like resistors and transistors. Essentially, it is the brain of any electronic device, processing data and controlling power in a very small space. It is a big win: compactness, lower power use, and better reliability. Next up, the multiplexer. This is a data selector. It takes multiple input signals and directs just one of them to a single output based on control lines. It is super useful for routing data, converting parallel signals to serial, and saving valuable real estate on a chip. Before manufacturing a chip, we have to test it virtually. That's where EDA tools comes in. We run three main simulations. First, logic simulation, using tools like PSPice to verify basic gates and flip-flop. Second, gate level simulation, which check the actual circuit netlist to see how components interact electrically. And third, pre-layout simulation, which use statistical analysis to predict how manufacturing variations might affect performance, kind of like a stress test before a chip is even drawn. Now let's look into analog IC design. Analog IC designs handles continuous signals unlike digital binary logic. The inverting OPM is key non-inverting input grounded, creating a virtual ground. Transient analysis over 3 milliseconds shows smooth sine wave. Input peaks at positive 1 volt, output drops at negative 2 volt, confirming linear phase inversion. Simulation match theory, verifying our design. The workflow design simulate, analyze, adjust, document. Now we move on to our first question. Each group was assigned a combinational logic circuit to design and verify. Our task was to implement an 8-to-1 multiplexer. A multiplexer, or MUX for short, is a circuit that selects one of the several input signals and forward it to a single output line. Specifically, an 8-to-1 MUX has 8 data inputs labeled I0 through I7, 3 select lines, S2, S1, and S0, and 1 output X. The truth table shows that select line determines which input is passed to the output. For example, when S2, S1, and S0 is 0, 0, 0, output X equal to I0. When it is 0, 0, 1, X equal to I1, and so on up to 1, 1, 1, which selects I7. From this truth table, we can derive the Boolean equation. It is a sum of 8 product terms, which each term corresponds to 1 select combinations. Okay, next, let's look at the Verilog implementation. We designed a molecule called MUX8+1 with an 8-bit input I, a 3-bit select input S, and output X. Inside, we use a case statement to assign the correct input bit to X based on the value of S. Here is a quick note. In the code shown, there's a small issue with where S is declared as a 3-bit input, but also redeclared as a 4-bit rack. In practice, we should keep S as a 3-bit wire inside a sensitive list, but the logic remains correct. The test bench set the input I to a fixed value of 8B00011100, then cycle through all the select combination from 0 to 7 with a 10 nanosecond delay between each change. This allows us to observe the output behavior. At the circuit level, this MUX is built using NOT gates to complement the select signal and gates to combine each input with its specific select combination, and a single OR gate to merge all the AND output into the final output X. This is a standard implementation of a multiplexer using basic logic gates. Now let's analyze the simulation waveform. With the input I set to 8B00011100, the select line change from 000 to 111 every 10 nanoseconds. Looking at the output X, we can see it follows the selected input bit exactly. When S is 000 and 0 or 001, the output is 0 because I0 and I1 are both 0. When S is 010 or 011 or 100, the output becomes 1 because I2, I3, and I4 are all 1. And when S is 101, 110, or 111, the output returns to 0 because I5, I6, and I7 are 0. This confirms that our multiplexer correctly selects the input specified by the select lines, validating both our theoretical design and our Verilog code. Moving on to question 2. We are given a combinational logic circuit with 3 input A, B, C, and 1 output X. The truth table is provided and we need to derive the Boolean equation, design the circuit, and verify it to simulation. From the truth table, we can see that the output X is 1 of 3, 1 for 3 input combination, when A is 0, B is 1, and C is 1. When A is 1, B is 1, and C is 0, and when all 3 inputs are 1. This gives us the Boolean expression X equal to A invert BC plus A BC invert plus ABC. These are the three product terms that correspond to the rows where the output is high. Now we can simplify this equation using a Karnaugh map. By grouping the 1 in the K-map, we can find that the expression reduced to X equal to AB plus BC. This is a much simpler form. This simplified equation tells us that the output is high whenever B is 1, either A or C is also 1. In other words, B acts as an enable signal. At the gate level, this circuit is implemented using just 2 AND gates or 1 OR gates. The first AND gate computes A and B, and the second computes B and C, and the OR gate combines them to produce final output X. It's a very efficient and straightforward implementation. The Verilog code for this circuit is simple and elegant. We define a module with inputs A, B, C, and output X. We use two internal wires for the AND gate outputs, then assign X as the OR of those two signals. This test bench applies all 8 possible input combinations with a 10 nanosecond delay between each exchange. It also includes monitoring and waveform dumping comments to capture the simulation results. The result waveform shows exactly what we expect. The output X become 1 only when B is 1 and either A or C is also 1. This matches our simplified equation perfectly and confirms that our design is correct. So both theoretical analysis and simulation verification are in complete agreement. Let's conclude our presentation. Thank you for your attention. Bye.